Dear friends, welcome to Rajshekhar classes on applied data science with Python. This is lecture number 365. In this lecture, we will try to understand gradient descent for linear regression. Let's take our linear regression formulation, which is this is our linear regression formulation. If you are not aware of this particular formulation, I will discuss in future classes. Time being, just understand W star, optimal value of W, which is equal to argmin of W, sigma I equal to 1 to n, yi minus W transpose xi whole square. So, if you notice here, I am not putting any regularization, no regularization, isn't it? So, no regularization. In this no regularization, in this formula also, in this formulation also. I am not using intercept term. What is my intercept term? W naught. W naught is intercept term. I am not using the intercept term, which is W naught, just for simplicity. Of course, you can do with regularization with an intercept term. This is what I want to minimize. Argument of W, sigma I equal to 1 to n yi minus W transpose xi whole square. How to apply gradient descent for this specific problem? So let's write down what is L here. What is L? L equal to, I can say, sigma I equal to 1 to n yi minus W transpose xi whole square, isn't it? Remember, here my xi and yi are part of D train. Just see, your xi, yi belongs to D train. Given a training data, they are constants. Which are constants? Xi and yi are constants. They are constants. So, now what is that you want to find? You want to find the best W. You want to find the best W, not the best X, isn't it? Not the best X. Here lot of people get confused. In this case, yi and xi are constants. Yi and xi are constants, isn't it? Y and x are constants because they are part of the data set. They come from training data. L is a function of W, isn't it? Just see, L is a function of W, and this is what you want to. This one you have to optimize. You have to optimize L of W, isn't it? How can I optimize that? What is the procedure? What can I do? This is the problem. What I have to do? Del of L with respect to W equal 0. This is the problem we have to solve. This is the problem. This is the problem we have to solve, isn't it? We have to solve. What del of L with respect to W? It's very simple. How can I calculate? This is my L. Instead of L of W, for simplicity, I am writing L. I am differentiating with respect to W. Sigma I equal to 1 to n. What is d by dx of x power n? That is n into x to the power of n minus 1. Therefore, I am differentiating with respect to W. Therefore, 2 into y I minus W transpose xi whole to the power of 2 minus 1. Again, internal differentiation with respect to W means yi constant 0. 0 minus W with respect to W1. I will get minus xi. That's what, minus xi. Isn't it? That is del of L with respect to W. Since I have my derivative, what I have to do? Step 1. Step 1 is I will pick a random vector. We should pick a random vector W naught. What is this W naught? Of course, W naught is a d-dimensional vector. It's a vector of how many dimensions? It's a d-dimensional vector. Once I pick a random value, we define W1 What is my W1? My W1 is equal to, yes, W1 equal to W0 minus R into, actually what is the formula? W1 equal to W0 minus R into dy by dx, isn't it? At W0, some R into dy by dx. It's a, but here it's a vector differentiation. Therefore, R into, what will I get this? Instead of dy by dx, I must write del of L with respect to W. That I have to replace. R into, in the place of dy by dx, I must write del L with respect to W. That's what we discussed in previous lectures. Therefore, R into del L with respect to W is this one. Sigma I equal to 1 to n minus 2xi into yi minus w transpose xi. That is W0 is, what is our W0? In step number 1, I will pick a random vector W0. Of course, W0 is a d-dimensional vector. Once I pick a random value, we define W1 as W0 minus R into sigma I equal to 1 to n. Well, how you got it? Because of this R into, what is the formula? R into, I must write, this is essentially W1 equal to W0 minus R into, instead of dy by dx, I must write del of L with respect to W. We already calculated del L with respect to W. That's what I'm substituting here, isn't it? Let's assume I change my R. I already discussed about what is R. Let's assume I change my R as a function of iteration number. What about my W2? My W2 is W2 equal to W1 minus R into sigma I equal to 1 to n minus 2xi into yi minus W1. As it is W2, it must be, as it is, just let me explain, as it is W1, it is W0. As it is W2, it must be W1, isn't it? Yes. We will compute W2 equal to W1 minus R into sigma I equal to 1 to n minus 2xi into yi minus W1 transpose xi. We will compute, what can we compute? Compute W0, W1, comma W2, so on Wk, comma Wk plus 1. If Wk plus 1 minus Wk is very small, if Wk plus 1 minus Wk is very small vector of small values, then I will say let's stop it here and declare, let's declare W star, my optimal value of W star is equal to Wk. This is what we will do. Our scikit-learn in Python. Scikit-learn writes this code, write this iterative code. Scikit-learn literally implements this. Look at, in any iteration, just let me say, in any iteration, Wj equal to Wj minus 1 minus R into sigma I equal to 1 to n minus 2xi into yi minus w transpose j minus 1 into xi. This is one problem with one major, there is one problem, actually there is, I can say there is one problem, there is one problem with this. What is that problem? One problem with this particular formulation, one major problem with this particular formulation is for every update, every time, I'm going from Wj minus 1 to Wj. Wj minus 1 to Wj, isn't it? W0 to W1, W1 to W2, something like Wj minus 1 to Wj. What you have to do? You have to compute this one. Sigma I equal to 1 to n minus 2xi into yi minus w transpose j minus 1 into xi. This particular summation is overall points. This is for overall points. If n is very large, if your training data set is very large, if n is very large, let's say your n equal to some 10 millions. 10 million data points, isn't 10 million, which is not uncommon in data science. Then we need to compute sigma I equal to 1 to n minus 2x into y minus w transpose j minus 1 into xi. Computing this piece here requires me to go through the whole data set, isn't it? Just computing this very, very expensive. If n is large, computing this summation is very expensive and time consuming. It's a time consuming process, whether you go from W0 to W1, whether you go from W1 to W2, you have to compute all this particular summation. For every W, we have to recompute whole thing, which means for every iteration, you have to go through the whole data, because sigma I equal to 1 to n is across your whole data. If you have millions of points, this is very, very time consuming, especially if n is large, which is not uncommon, which is fairly common in data science. When n is large, then what do we do? So there is actually solution of gradient descent can become very, very slow, isn't it? Solution of, I can say, if n is large, solution of what? Gradient descent. Gradient descent can become very, 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 very slow. Very, very slow if your n is large, isn't it? To solve this problem, optimization experts and mathematicians came up with a technique called, what is that technique? Stochastic gradient. Stochastic gradient descent. Stochastic gradient descent, which is very, very a beautiful hack. It is, I can say, it is a beautiful hack. It is a beautiful hack. Probably one of the beautiful hack that I have seen in optimization, wherein you don't have to go through the whole data, but eventually you get the same result. So we will see the stochastic gradient descent in the next lecture. Just go through this particular lecture. This particular lecture is very, very important to understand my next lecture, that is SGD. SGD means stochastic gradient descent algorithm. Thank you very much.